Hi, I'm Richelle Buenaventura, and I'm discuss Object-Oriented Programming 1. Introduction to Objective-Oriented Programming. Objective Object-oriented programming is a programming paradigm which is centered in the use of objects. Objects are representations of tangible and intangible materials that passes some level of information. These objects can be anything from day-to-day materials we use to classification like the Congress. The only thing that limits them is the information that they should possess for us to implement afterwards through programming. Advent of object-oriented programming. The practice of object-oriented programming came as early as the year 1967. In that year, a programming language, Simula, used features which we regard now as the fundamentals of object-oriented programming. The Simula is a programming language which is specialization on simulations. It was developed by Ole Johan Dahl and Kristen Garg at Norwegian Computing Center in Oslo. Alan Kay, Alan Kay, working at the University of Utah, used the features present in Simula as inspiration to come up with the idea of object-oriented programming. This idea was completed at Xerox PARC when Alan Kay led a team after the transfer to Xerox PARC. At Xerox PARC in early 1970s, object-oriented programming as a programming paradigm was born. Dynabook was the first personal computer that was created using object-oriented programming. Smalltalk was the object-oriented programming language built specifically for Dynabook. Since then, the object-oriented programming as a programming paradigm became popular. This inspired Bjorn Stroop to integrate this paradigm to the most popular programming language of 1980s, C language. This gave birth to C++ as a programming language that supports object-oriented programming. Principles of objects. To better understand the object-oriented programming, you need to understand about the core of object-oriented programming. The objects are simply representations of something that is built by information. Take a book of an example of an object. A book is represented by title, author, year of publication, and publisher. A book is composed of pages. Pages can be thought of as another example of an object. A page has page numbers, paragraphs, chapter title, and subtopic titles. Let us choose a box as an object. A box has color, width, height, and volume. In addition to that, we can store other objects into a box like the book in our previous example. The concept behind objects in object-oriented programming is the same is the same. An object has properties like the color, width, height, and volume of the box. An object has methods also which simply are just functions that are centered within the object. A method can be anything like get width or get height functions for our box object. Subsets of object-oriented programming. Now that we can Now that we have covered the fundamentals of object-oriented programming, we need to focus on how object-oriented programming was implemented in C++. There are two basic categories under object-oriented programming. There are follow: prototype-based and class-based. Prototype-based is a subset of object-oriented programming which focuses on reusability of objects in terms of extending initial state to a further defined state. In this design, prototype is created by the developer, which will be copied and modified during runtime to represent the final state of the object. It truly represents, think of it like a blank book. A developer creates a blank book in his source code. The blank book contains all necessary information like the subject and a temporary author, publisher, and year of publication. During runtime, the blank book will be populated with additional information through its methods. The information may come from user inputs or the database. Class-based is a subset of object-oriented programming which focuses on abstract representation of the objects. Abstract representation means there is no initial data present in the object definition. In this design, the objects may share the same properties and methods. However, as compared to prototype base, these objects are copies of their base object and not all throughout new objects. Class-based C++. The idea behind the class-based C++ revolves around classes. Classes are an abstract representations of an object. By themselves alone, classes are not objects. You can think of them as plans of the object that have properties and methods. The properties do not have yet data. In Figure 1, we will explore the structure within a class. The provided source code is named box H. A short discussion of header files. C++ header files are separate files in C++ structure where extra codes were placed supplement the main application. Another use of header files is the reuse, a huge range of source codes for different applications. However, header files are not convertible to C++ applications. Box header file in Figure 2 shows a snippet of box H, which focuses on the class structure definition of the box class. The declaration started with the class box statement. Following that is the scope declaration public. There are three scope declarations, namely public, private, protected. In Table 1 summarize the limitations of scopes is C++. Public scope makes the properties and methods under it accessible to anywhere within and outside the class. Private scope limits the access to the properties and methods under it only the class where they are defined. Protected scope limits the access to the properties and methods under it to the class itself and to all classes that inherits it. In Figure 3 shows the property and method declaration in our box class. As you can notice, the properties are simply variables within classes. They are declared similar to how variables are declared within the int main function. We define four properties under the box class, namely char color, int length, int width, int height. In addition to the four properties, we have two functions within the box class, namely constructor box, int length, int width, int height, int get volume. A constructor is a special non-prerequisite function named as the class itself that is created to initialize several properties of performed operations for the class upon declaration. A class can contain more than one constructor provided no two constructors has the same number of parameters. And we have an int get volume functions. As you can notice, we did not have any code block under the two functions. This is to promote code readability since we are only declaring the scope, function names, and parameters of the functions. In figure 4, we have the code block of our constructor notice. Notice how the constructor is structured using box. Int length, int width, int height. We use the box label to dictate that the box int length, int width, int height constructor is part of the class of the box class. The constructor simply assigns values to the two properties of our class. Lastly, we have the body for our get volume function. Since we want to declare that the function is for our box class, we append box, the class name followed by, within the function, we return the product of our length with height properties. Int main function. Now that we have a working class in our box header file, we need to use it in our int main function. Notice that we have added a new library box to our main CPP file. We use quotation marks to indicate that our box H library is located in the same file path as our main CPP file. Had we used the conventional greater than and less than symbols, the IDE and the compiler will search for the said library in the default library of our C++ files. Usually, in our installation folders, we declared a variable to have a box data type. This is the same as if we are saying that the box variable will use the box class. In addition to that, since we added a constructor to our box class, we called that constructor during the same time we declared the box variable. We passed the constants 2, 3, and 4 as our values to the parameters length, width, and height respectively. Lastly, we call the getVolume function of our box class and display them back to the user. Notice how we call the said function. We use the variable name followed by a period, then the function name like box getVolume. Object-oriented programming 2. Principles in object-oriented programming. Since the last module, we have talked about the world of object-oriented programming. We covered the essentials of object-oriented programming, which enable you to write OOP applications in C++. However, the journey in the world of OOP does not stop there. There are 4 principles behind OOP that you need to learn and how it applies in your current knowledge. These principles form the core of object-oriented programming. They serve as the heart of OOP such that without them, OOP is just a simple non-deterministic programming paradigm. These are 4 principles: encapsulation, abstraction, inheritance, polymorphism. Note that these principles do not overlay the fundamentals of object-oriented programming discussed in Module 10. In fact, these principles both strengthen and extend those fundamentals to achieve a complete programming paradigm. Encapsulation. The principle of encapsulation is to hide the internal working of your application. Encapsulation ensures that only the necessary methods and properties are presented outside of the current class. This principle is initially enabled using scope. Remember that there are three scopes in C++, namely public, private, and protected. These scopes limit the visibility of the properties and methods from outside of the class and outside the inheriting class. In addition to scope, we have accessors and mutators, which limits the actions done in properties and by extension including methods. Accessors. An accessor is a method within the class that enables the retrieval of values hidden by scopes. For example, if we hid the property int MyID under the private scope, we cannot access the property from outside of the class. To let the user, for example, retrieve the value stored in the int MyID property, we can use an accessor. Before tackling how to write accessors, we need to enumerate several characteristics of accessors that must be observed. These characteristics are follows. Accessors are methods with the return type like the data type of property. Accessors are parameterless methods. Accessors should never assign values to its reference properties. Accessors are prefixed with get in their function's name. As previously discussed, accessors are simply methods that enables the retrieval of values. Since an accessor is a method for retrieving values, it must have a non-void return type. Its return type solely depends on the data type of the hidden property it references. For example, we have a int MyID. Under the private scope, its corresponding accessor should have the return type of int. Subsequently, accessors are for retrieving values only. Its method declaration should never contain any parameters since the value to the return is not dependent on any other factors aside from the reference property itself. Adding parameters to accessor is unnecessary since the parameter should never affect the value of the reference property. In addition, accessor should never assign values to any of the properties, especially the reference property. Doing so, doing so defeats the purpose of accessors and might cause a call for integrity check. An integrity check is a test conducted to validate the values of properties in classes throughout the execution of the application. The idea behind integrity checks is to determine whether there exists a discrepancy between the actual values of the property and the expected values of the same property. Lastly, accessors are prefixed with get in their function name to indicate that those methods are indeed accessors. For example, if we are to write an accessor for our int MyID property, its equivalent accessor should be int getMyID method. Implementing accessors. We will look at a sample implementation of accessors in C++. For this example, we will be using a variant of our previous box example back at Module 10. However, we will modify portions of the code to accommodate changes to showcase the implementation of accessors in C++. In Figure 1 shows a variant of our box header file which has private properties. In this example, we move all the properties to private scope. Because of this, we cannot anymore call any of the properties. Example, int length. In our int main function, to provide read-only access to our private properties, we implemented accessors. In figure 2, pictures a snippet of our box header file. In this snippet, we have added a new function under our public scope, the intGetLength method. Notice that our intGetLength method has a return type of int similar to the data type of length property, does not have any parameter, and is prefixed with get is the function name. This so far complies with the characteristic of accessors. Now let us look at the implementation of our intGetLength method. As shown in figure 3, our intGetLength method simply returns back the value of our length property. There are no other operations done within the accessor. Hence, we fully completed the characteristics of an accessor. Mutators. Now that we have a method to retrieve values from our hidden properties, we also have a way to assign values to our hidden properties through mutators. Mutator is a method within the class that enables the assignment of values to our properties hidden by scopes. For example, if we hid the property string color under the private scope, we cannot anymore assign values to it directly. In this case, we will be using an intermediary which will assign values to it, the mutator. Like our accessor, mutators are bound to several characteristics which help define their purpose. These characteristics must be keenly observed. Mutators have one parameter. Mutators may or may not return to the final assigned value. Mutators are prefixed with set in their function name. The main purpose of our mutator is to store values to our hidden properties, and that only. Therefore, we set only one parameter, the process or unprocessed value we will assign to the property. Process values are values that have been through several operations which change the original value to the current value. Unprocessed values are values which have yet to be modified. To better understand the difference between processed and unprocessed values, we need to look at an example. For example, I have a string value of 0100 and I want to assign that value to an int variable. As of now, the value is still unprocessed since it has not yet been through any operation. Now, when I assign this value to the variable, since the variable is of int data type, computer programming, object-oriented programming 2+7 course module, need to convert the value to int. The converted value then becomes our process value. Converting a value from one data type to different data type is called casting. In addition, the mutator may or may not return the assigned value. This solely depends on the developer's discretion. However, it is advised to return the value if and only if there were some operations conducted before the value is assigned to the property. In our previous example of a string value to be assigned to an int variable, since there will be conversion of data type about to take place, the resulting int value should be returned. If the value will be assigned to the property directly without any conversion or processing, then there is no need to return the value. Lastly, mutators follow a naming convention to a fixed set in their function name. This is to convey the use of the method without the need of documentations and comments. Implementing mutators. We look at an implementation of accessors in our previous implementation. This time, we will look at a sample implementation of notators. For this example, we will use again our sample from Module 10, the box class. In Figure 4, we look at a variable of the box class that implements the idea of both accessors and mutators. Notice we have added a new method void set color string, which based on the naming convention used will assign a value to our string color, property hidden under private scope. Let us dissect this variant of our box class. In Figure 5, we note that the string color property is declared under private scope. This makes the string color property inaccessible outside of the class and by the inheriting class. Our added method declaration is placed under the public scope. This is to ensure that our mutator is accessible anywhere inside and outside of the class. We have placed one string parameter under our mutator which is similar in data type with the concerned property string color. Let us now look at the implementation of our mutator. Abstraction. Another principle in object-oriented programming is the abstraction. Abstraction is the generalization of classes and types to emphasize their functionality and interfaces over their implementation and details. These principles work together with encapsulation since both focuses on making the internal workings of the classes hidden from outside of the class. This is to make the class and its properties and methods to be self-descriptive of their task. One of the ways to implement abstraction is using scopes. Remember that the scopes limit the way any other classes and functions interact with the properties and methods of a class. This way, in the perspective of init, for example, can only see the methods under the public scope. Inheriting classes can see properties and methods both under the protected and public scopes. Inheritance. Third of the four principles in object-oriented programming is the inheritance. Inheritance is the means to extend the features and functionalities of existing classes and interfaces. In this principle, there is a prerequisite of at least one existing class or interface. An interface is a class in C++ which has methods that are virtual in nature. Virtual means that the method is not implemented wheresoever inside of the class. In simpler terms, there is no code blocks under those methods. In Figure 6, we have implemented an interface called iBox. Notice that iBox only has two methods and both of which are under the public scope. These two methods were defined as a virtual methods, hence, there were no implementation of those methods anywhere in the source code. In addition, we have added equals 0 after the method declaration to signify there are pure virtual. A pure virtual method is a method in the class that needs to be implemented by the inheriting class. Since this class only contains virtual methods, this class is said to be an interface. We had yet another version of our box example shown in Figure 7. In this box class, we have inherited the iBox interface we defined in Figure 6. Notice how we implemented the inheritance through the class declaration statement class box. Public iBox. In this line, we have inherited all properties and methods of the iBox interface. Since the iBox interface contains two pure virtual methods int getValue and string getColor, we were required to implement the two methods inside our box class. The class principle of object-oriented programming that we will cover in this course is polymorphism. Polymorphism is the principle of object-oriented programming that deals with different variations of the same method. This function uses the same function name. They only differ in the combination of data types used in their parameters. For example, we have the sum function. This function shall accept two inputs in its parameter. Since we cannot force the use of the sum function to be limited to integers only, we need to polymorph the function. In our sum function example, we can create several variations of that same function. If we need to add two integers, we can declare a int sum function. If we need to add two floats, we can declare a float sum float function. If we need to add the three integers float sum, we can declare int sum and float sum function. In figure 8, we can see four variation of the sum function. We supported the combination of 2 and 3 parameters for both int and float data types. These are two forms of polymorphism and the overriding and the overloading. Overriding. Overriding is the polymorphism that occurs during compile time. Overridden methods are the common structure of polymorphism. It considers the current form of the functions. In this type of polymorphism, we had the function call upon the existing function and overlap their statements with another. This is common in inheriting classes wherein the parent class has an existing method and the child class overrides the existing method to perform a different set of functions. For example, we have a parent iBox interface from figure 6. In the figure, the iBox interface has two methods, string getColor and int getVolume. Then in figure 7, the box class inherited the iBox interface. In doing so, box class also inherited the right to the two methods of iBox interface. Box class implemented the string getColor and it getZipVolume methods. In this case, the two function of iBox was overridden by the functions of box. Overloading. The second form of polymorphism in overloading. Overloading occurs during the runtime. In this form of polymorphism, the functions are given different parameters but share the same function name. These functions usually reside with the same source code. Figure 8 implements this form of polymorphism. Notice how the sum functions are repeated and structured differently from one another. This variation is a sum functions for two integers. The second variation is a sum function for three integers. The second variation, also called the first variation of the sum function. The third variation is a sum function for two floats. The class variation is like the second variation. The only difference is that the class variation is for three floats. Now we discuss it's all about pointers and references 1. Introduction to Low-Level C++. Since the start of the course, we have explored the C++ programming language in its beauty as a high-level programming language. We have altogether explored the conditionals, looping, arrays, functions, and object-oriented programming schemas of C++. Ideally, programming languages are categorized in terms of complexity by high-level programming language, low-level programming language, mid-level programming language. High-level programming language. High-level programming language are the easiest category of programming language to work with. High-level programming language are programming language that exhibits the strongest abstraction of its programming schema. High-level programming language enables developers to focus on the logic of the application they are developing. They, they take away the obscure details of how to implement the technical aspects of what they are developing. In addition, they automatically manage the memory allocation part and resource disposal aspects of the development. High-level programming language also limits the control of the developer over the operating system. This is to fully manage the instructions that come and go to the operating system's instruction set. This part of high-level programming language is essential which allows the developer to construct their logic without bothering with too much about how to manage overflowing memory and proper resource disposal. Low-level programming language are, in contrast, the hardest to manage of all the categories of programming language. Low-level programming language are programming language that exhibit the weakest abstraction of all the programming language aside from machine language themselves. Low-level programming language also enables the developer to get into detail of how they like their logic to be implemented. Low-level programming language can give access to even the hardware components of the computer and the inner workings of the operating system. They can manage and manipulate the runtime task that the current running operating system is working on. Low-level programming language also lets the developer explore the world of embedded systems, giving them access to even the smallest component in the environment. Developers are given direct access to the memory of the computer, particularly the random access memory. They can also manipulate the values stored in other memory sectors. There exists the least limitations passed to low-level programming language. Mid-level programming language. Mid-level programming language are the go-in-between of the other programming language. Mid-level programming language are programming language that exhibit strong abstraction and mid-range access to the memory and operating system. Mid-level programming language showcase user-friendly implementation and structures. Majority of the features available to low-level programming language are hidden in the background and are usually taken for granted. Some of the implementations are hidden from the user. In addition, some of tasks are designed by the programming language to the abstract. C++ programming language. The programming language designed by George Strostrup in 1979 was initially proposed as a high-level programming language. The inner workings of C++ are hidden from the developer through its wide range of libraries and features. Even the conditionals and looping statements do not exhibit what will originally be considered as a low level in detail. This is mainly because the developer is limited to the access and conditions that are present where performing such executions. However, due to the advent of the recent high-level programming language like Java, C Sharp, and Visual Basic Net, C++ are also considered to be a low-level programming language. This is supported by some level of access that C++ give the developers. C++ enables the developers to get in detail the memory sector of the computer. In addition, there are a lot of memory-specific features that only C++ has. This is further supported by the fact that the original C is a low-level programming language. Since C++ is by extension an extended version of C with the support of object-oriented programming. Introduction to pointers and references. Now that we have established the fact that C++ can be considered as a low-level programming language, we need to dwell on one of the infamous low-level capability of C++, the pointers and references. These features of C++ coupled with dynamic memory allocations form the fundamental of C++ being a low-level programming language. Pointers. Pointers are special variables in C++ that points to a sector in the memory. These variables are used as companions of other variables. They extend the coverage of the variables to such a point that original variables are being accessed from different sectors of the code without being recreated and reassigned. In this point, the concept behind pointers might not be too clear. As seen as figure 1, we had declared a variable int myid and a pointer int. You can see figure 1 myid variable and ptrld pointer. In figure 2, C++ programming language pointers represents references and dynamic memory allocations. References. We had used the address of operator to retrieve the address of variables. In addition to that, we can also use the address of operator like pointers. That is reference. A reference is a special variable which, like pointers, stores the address of a variable. The main difference is that the address stays permanent, whereas pointers can change the variable where they point to. In figure 3, variables myid and your ID and reference ref ID. Later in the code, we use the value of the reference in ref ID, followed by the changing of the value of int variable. It's all about pointers and references too. Variable pointers and references. In the previous module, we covered using pointers and references in variables. This time, we will go on in depth with how a pointer variables and reference variable work. Difference. Table 1 is a difference between variables, pointers, and references. Declaration. We start off with the declaration of variables, pointers, and references. Since we have been dealing with variables since Module 4, the behavior of variables when declaring them are not surprise. Data type. Next, we cover the effects of the data types to the variable pointers and references. Initialization. Initialization is the phase wherein a variable pointer and reference are assigned their default or initial value. Variables and pointers behave the same references, only differs from the two. Values stored. Variables behave differently from pointers and references. Variables store the actual value it is supposed to store. The memory allocated to it hold the value stored to the variable and not elsewhere. Variable reassignment. Variable reassignment occurs when a variable is being assigned to a pointer or references. Reference. The same structure is followed like the initialization stage. The only difference is the location where the assignment occurs. Variable reassignment occurs after the initialization stage. Assigning a variable. Assigning a variable is like the next subtopic. Assigning a value. Assigning a variable means a variable is used to the assignment operand. As retrieving the value using standard method. Retrieving the value using standard method is the conventional method to retrieve the value. It does not use any other symbol aside from the variable name itself. Retrieving the value using the differencing operator. Retrieving the value using the unary, unary operator. The unary operand stands for the differencing operator. This operator returns the value of the variable pointer is pointing to. Function pointers and references. It is also possible to use pointers and references in functions, particularly in the return type and the parameters. This is mainly because a function is just a separate code block that contains its own set of statements which are focused on replicability. Pointers in the parameters body. To implement pointers references relation in function, we first invoke some of our parameters to be pointer. This process is like how we declare variables as pointers. We simply append the